500,000 kilograms in the air for 15 hours straight. That number does not make sense. And yet it happens every single day, thousands of times, all over the world. So the real question is, why does physics allow it at all? Because here is what most people do not realize. An airplane does not fight gravity. It uses something else entirely. And the moment you understand what that is, you will never look at a takeoff the same way again. Let us start with the scale, because it matters. The Airbus A380, the largest passenger aircraft ever built, has a maximum takeoff weight of around 575 metric tons. That is roughly the weight of a fully loaded freight train. Not a car, not a truck, a freight train. And this machine does not just barely get off the ground. It climbs to 40,000 feet and cruises at 560 miles per hour for up to 15 hours without stopping. By common sense, something that heavy should never leave the ground. But common sense is wrong here. And here is why. Every airplane in flight is controlled by four forces. Weight is gravity pulling it straight down. Lift is an upward force generated by the wings. Thrust is the engines pushing it forward. And drag is air resistance pushing back. When lift equals weight, the aircraft holds altitude. When thrust equals drag, it holds speed. The moment one of these forces shifts, everything changes. It is not magic, it is not defying physics, it is physics working exactly as it should. But that raises the actual question: where does lift come from? You have probably heard the standard explanation. Air over the top of the wing travels a longer path, so it moves faster, creating lower pressure, which pulls the wing upward. That explanation is taught in schools. It is also incomplete. In some cases, it is just wrong. Here is what actually happens. A wing has a specific shape, curved on top and flatter underneath. During flight, the wing is angled slightly into the oncoming airflow. That angle is called the angle of attack. As air flows around the wing, the flow over the top surface accelerates. Pressure above drops. Pressure below stays higher. That pressure difference produces an upward force. But that is only part of it. The wing also deflects air downward. According to Newton's third law, if the wing pushes air down, the air pushes the wing up with equal and opposite force. Bernoulli and Newton are not competing explanations. They describe the same event from two different angles. Lift is the result of both the pressure difference and the downward deflection of airflow. Together, they hold hundreds of tons in the sky. But here's where it gets interesting. The pilot controls how much lift the wing generates in real time during flight. The key variable is the angle of attack. When a pilot pulls back during takeoff, the nose rises and the angle of attack increases. The pressure difference across the wing grows, more air is deflected downward, and lift increases rapidly. But there is a hard limit. Push the angle of attack too far, and the airflow over the upper surface can no longer stay attached to the wing. It separates. Pressure distribution collapses and lift drops suddenly and violently. That's a stall. Avoiding it is one of the most critical jobs a pilot has. Speed is the other half of this equation. Lift depends on velocity and not linearly. In the lift equation, velocity is squared. That means if you double the speed, lift increases 4 times. Cut speed in half and lift drops to 1/4. This is why an aircraft cannot just roll onto the runway and slowly rise into the air. It must accelerate to a specific minimum speed before the wings can generate enough lift to equal the aircraft's weight. Only at that exact moment does the aircraft lift off, not because it became lighter, but because the aerodynamic forces finally caught up to gravity. Now, what about low speed? Takeoff and landing require the aircraft to fly slowly, but the wing generates less lift at lower speeds. So how does that work? This is where high-lift devices come in. If you have ever sat by the window and watched the wing before takeoff, you have seen it. The wing changes shape. Flaps extend from the rear edge. Slats extend from the front, creating a narrow slot between the slat and the wing. This does three things at once. It slightly increases the effective wing area. It significantly increases the curvature of the airfoil. And it dramatically increases the lift coefficient, which is the wing's ability to generate lift at any given speed. The slats do something especially important. The slot they create allows high-energy air from below the wing to flow over the upper surface, helping the airflow stay attached even at high angles of attack. This delays the stall. That is why aircraft can safely operate at much lower speeds during takeoff and landing without losing control. So why do airliners cruise at 35,000 to 40,000 feet? Here is what most people miss. At that altitude, the air is thin, much thinner than at sea level. Drag depends directly on air density. The thinner the air, the less resistance the aircraft encounters. Less drag means less thrust required, and less thrust means less fuel burned per mile. The engines also perform more efficiently in the cold, thin air at altitude. There are fewer weather systems up there, and less turbulence from terrain and surface heating below. As the flight continues and fuel is burned, the aircraft becomes lighter, and it can climb even higher, a technique called step climb that squeezes out every last fraction of fuel efficiency. But here is what all of that means at a deeper level. The aircraft is never just sitting in the sky. It is continuously interacting with the air around it. Every second of flight, an enormous mass of air flows around the wings. The aircraft gives that air downward momentum. The air gives the aircraft upward momentum in return. Lift is not a passive force. It is the constant, active result of the aircraft reshaping the airflow around it, thousands of times per second. That is the real answer to how a 500-ton machine stays in the air. It does not defeat gravity. It earns lift, continuously and precisely through aerodynamics, speed, angle, and shape, all working together in a system that has been refined over more than a century of aviation engineering. And here's the part that still gets me. The next time you watch a fully loaded A380 lift off the runway, that enormous machine carrying hundreds of people and hundreds of tons of fuel and cargo, it does not jump. It does not struggle. At a very specific speed, the runway simply stops being necessary. The ground lets go, and physics takes over. That is not magic. That is engineering so well understood that it works the same way every time, all over the world, hundreds of thousands of times a day. And now you know exactly why. If you have ever wondered how that same aircraft actually stops after landing, that is a whole different system, and it is just as surprising.